This is section 2.2 of your text, Polynomial Functions of Higher Degree. Recall that the text is Ron Larson, Precalculus, 11th edition. Characteristics of the graphs of polynomial functions. We're going to start by taking a look at what the graph of a polynomial function looks like. So I have y equals x squared, y equals x cubed, y equals x to the fourth. So basically I have the monomial version or the one-term version of each of the degrees from 2 to 7. So a polynomial, we've already talked about the fact that a quadratic is just a special polynomial. That's that one of degree 2. And we know different forms for that, but we want to broaden our horizons a little bit into all of the polynomials. So you can see that a polynomial is going to have a degree of n, and n sort of tells us what the graph's going to look like. So in this case, n would be 3, here n would be 4, and so forth. What they all have in common is that the graph is continuous. So if I click on any of these graphs, that's the squared, that's the cubic graph, this is the quartic graph, and so forth, I can click on any of them that I want and scroll in or out, and you can see very clearly that there's no holes or gaps. You can also see that we only have smooth, rounded surfaces, so we don't have any sharp corners or anything like that. Even functions, 2, 4, 6. Notice those are pointing in the same direction at the beginning of the graph and at the end of the graph. So if the leading coefficient is positive, they're pointing up. But if I did the same functions but put a negative in front, each one is going to just flip right over. And that's for all of the even functions. Now for the odd functions are always going to begin and end in different places. So the standard way that they're going to begin and end, that means when there is a positive coefficient, just like a normal linear equation, it will be down to the left and up and to the right. Just like I did with the even functions, if I give you a negative coefficient, it's going to flip that order. So instead of down to the left, up to the right, it's up to the left and down to the right, kind of like a negative slope. We can also use all of those same transformations we had before. So let me get rid of a couple of these. If I give you a number from 0 to 1, it's going to make it fatter. If I give you a number greater than 1, or the absolute value is greater than 1, it's going to make it skinnier. I can get rid of that negative and make it go the correct direction again. And all of those transformations we did before. Minus 8, we can see that brought it down 8. If on the inside I put x plus 3, that's going to take it to the left 3, and so forth. So all of those same things that we've been learning should all come together here in the graphs of polynomials. Another aspect of the graphs that we're really going to want to know is how to find the zeros of a graph. So if you'll recall, a zero of a graph just means that the point at which the graph is going to cross the x-axis, or the point which is an x-intercept, so x value comma 0. So we're just going to review, or maybe learn, if you don't know these, some facts before we review factoring. So one fact, the graph of f has at most n minus 1 turning points. So if you'll recall, n was the greatest degree. So when I had a quadratic function, I always have a parabola. That means it has one turning point. If I have a cubic function can look like this, 1, 2 turning points. You get the idea, n minus 1 turning points. A function f has at most n zeros. So if I'm dealing with a quadratic function, look, I can have 1, 2 zeros, or I can have no zeros because it doesn't cross the x-axis at all and would be imaginary values. However, if I have a function of odd degree, so 3 or 5 or 7 or so forth, I must have at least one. And that should make sense to us because of the way the graph looks. I have to have at least one 0. Because if it wasn't here, whoops, it would have to be up here, right? And it doesn't matter if it's going up from left to right or down from left to right. None of that matters because we know it's got to cross at least one time. A 0 that is repeated k times has a multiplicity of k. So if I'm dealing with a function of even degree, like y equals x squared, if I have a multiplicity of 2, that means my graph is actually going to come to the x-axis, turn right there, and go in the opposite direction. Whereas if I have a function of odd degree and it has a multiplicity of 2, it's still going to go in the opposite direction, but you might see it sort of level out just a little bit right there. Lastly, the following statements are all equivalent. So any of these things that we're going to talk about all mean the same thing. X equals a is a 0 of the function. X equals a is a solution of the polynomial function f of x is equal to 0. X minus a is a factor of the polynomial f of x. Or a comma 0 is an x-intercept of the graph. So we talked about the fact that a 0 is where it crosses the x-axis. It's an x-intercept. We're going to be working on factoring, and that's how we're going to factor. It's factoring in order to find those x-intercepts or zeros or solutions of the polynomial function. So let's get started reviewing factoring. Before we practice factoring together, I did want to provide you with this very clean list, so I'm not going to write on this screen at all, so that you can take a screenshot, so that you remember the steps in which you should follow in order to factor. The first step is to find the GCD, greatest common denominator. So if you can take 2 out of every term, or 2x out of every term, or anything out of every single term, you should do that first. 2, you're going to factor based on the number of terms that you have. So if you have 2 terms, there are certain ways that you can factor. 3 terms, there are certain ways, and 4 or more terms, there are certain ways. And we are going to practice all of those together in the following slides. We'll begin by factoring a GCD, or greatest common denominator, and taking a look at strategies for factoring 2 terms. If you'll notice, I already have both of these set equal to 0. So if you start with a binomial, trinomial, and so forth that's not set equal to 0, that should be a first step. I didn't include it on the list, but possibly should have. The first step on my list is to find the greatest common denominator. So if you have 2 values, or 3 values if you're dealing with 3 terms, that all have a common denominator, or a term that you can take out of each one, you should do that. So for instance here, I have 5x squared and I have 25x. So I can take 5 out of both of those terms, and I can take an x out of both of those terms. And I'm going to move that down just a little bit to give me some room. What that means is if I take out a 5x, I'm really just dividing each term by 5x and writing what's left over. So my 5's cancel, one of the x's cancel, I'm left with x. 25 divided by 5 is 5, and those x's cancel. That's it for factoring on my first term. Now keep in mind, if I just need to factor, I'm done with this question. If it says find the zeros or find the solutions to the polynomial function, well then I'm just going to use the zero product property that says when you multiply 2 things that are equal to 0, one or the other must be 0. So I'm going to set each of those factors, which is 5x and x minus 5, both equal to 0, to find that the zeros are x equals 0 and x equals negative 5. And I'm not going to graph any of these today, but feel free to get out your graphing utility, go to Desmos or your calculator or anything else, and plug in this function, and it should look like a quadratic function that goes through at 0 and at negative 5, and it should be pointing up, and that's all I'm going to do for now. For my second function, again, I'm going to start with the greatest common denominator. I can see that I can take a 9 out of both of those functions, or sorry, both of those terms, but I can't take an x out because 81 doesn't have an x. That leaves me with x squared minus 9. Now, on the first question I did, if you'll notice, this was x to the first power. That's how I knew my factoring job was over. And as you can see here on my second example, I still have x squared. So now there's two ways to go about finishing this question. One way is to use the difference of squares pattern. And the difference of squares pattern says if you have two terms and they're both perfect squares. So can I take the square root of x squared? Yes, the square root is x. Can I take the square root of 9? Yes, the square root is 3. If I can do that, then I can rewrite my function as the square root plus the square root and the square root minus the square root. And I would be done if all I needed to do was factor. If I needed to find the solutions, just as I did before, I would set everything equal to 0. I don't have to set 9 equal to 0 because there's no x term. So x plus 3 equals 0, x minus 3 equals 0. That gives me x equals negative 3 and x equals positive 3. Now the other way, and I would use the other way if I were only asked to find the solutions, but I don't need to actually factor. So if it didn't say factor, it just said find the solutions or find the zeros, then you could use the opposite way that says, okay, now that you have factored this into 9 and then x squared minus 9 is equal to 0, go ahead and use that zero product property to set x squared minus 9 equal to 0, and now separate the terms by the equal sign and solve. So add 9 to each side, take the square root of each side, and I get x equals plus or minus 3. You'll notice that's the same answers I got using the other method. Now let's look at factoring with three terms. We're going to handle it a little bit differently if a is equal to 1 or if a is not equal to 1. So on this page, we're just going to forget about a not equaling 1. We're still going to use the greatest common divisor if we have it, but then we're going to look for, if a is 1, we're going to look for factors of c with a sum or difference of b. So let's look at our first question together. We have x squared minus 5x minus 36 equals 0. We know that a is 1, and that's good because that's what we're using now. B is negative 5. C is negative 36. So what I'm going to do is I'm going to look for factors of C. What numbers multiply to 36? I'm not going to worry about the negative yet. 1 and 36, 2 and 18, 3 and 12, 4 and 9, 6 and 6. All of those multiply to 36. I need their difference to be 5. So I need their difference to be 5. I actually need their difference to be negative 5, but for now I'm not worried about the negatives. So the difference between 1 and 36 is 35. Between 2 and 18 is 16. Between 3 and 12 is 9. Between 4 and 9 is 5. And between 6 and 6 is 0. So I know I'm going to be using 4 and 9. And now this is where the negative comes into play. When I multiply 4 times 9, I need to get negative 36. So one of them has to be negative. When I add them, the sum needs to be negative 5. So it makes sense that the 4 will be positive and the 9 will be negative because that would add together to get negative 5. That means my factorization is x plus 4, x minus 9 is equal to 0. And then, of course, I could just use the zero product property to say x is negative 4 or x is 9. So again, this is the factorization. These are the zeros or solutions. Let's look at the second one, and if you're feeling comfortable with it, go ahead and try it on your own. The first thing I would do is move everything to the same side. We always want it equal to 0, and we'd prefer that leading coefficient to be positive. So 33x cubed minus 33x squared plus 84x equals 0. Now it looks like each of these has a term of 3x that I can factor. So I'm going to divide everything by 3x, leaving me with 3x, and then x cubed divided by x to the first leaves me with x squared, This gives me 11 and then x to the first, and this gives me 28. So now, again, I'm looking for numbers that multiply to 28, factors of 28. So 1 and 28, 2 and 14, 3 doesn't go into 28, 4 and 7, and that's all I can come up with. Now, before we wanted a difference of 5, and we needed a difference because we were looking at minus 36. Now I want a sum of negative 11. So when I add them together, this would be 29. That doesn't work. When I add these together, that would be 16. That doesn't work. When I add these together, I do get 11. And again, there needs to be a sum of negative 11, so they're both going to be negatives. So my factorization is 3x, from taking the 3x out before, and then x minus 4, x minus 7 is equal to 0. My solutions, so that's the factorization, my solutions are x equals 0 from setting 3x equal to 0. X is equal to 4 from setting x minus 4 equal to 0, and x is equal to 7 from setting x minus 7 equal to 0. Now let's take a look at factoring 3 terms when a is not equal to 1. So again, this is going to be a little bit different than what we did before. When we have 3 terms and a is not equal to 1, I use amazing factoring. Now I know there are about a dozen or more ways that people have come up with for here's a strategy for factoring. And if you have one and it makes sense to you and you're good at it, then you should use that. If you're not good at it, you have no idea what you're doing, you have no idea what factoring even is, stick with me and we'll try to get through this together. What we're going to do for amazing factoring is we're going to look at a, which in this case is 6, not 1, b, which in this case is 1, and c, which is negative 2. We're going to start by finding a times c. So in this case, 6 times negative 2, which is negative 12. So kind of like what we did before when we said, let's look for numbers that multiplied to c. Now we're looking for numbers multiplied to ac. So what numbers multiply to 12? So I have 1 and 12, 2 and 6, 3 and 4, and that's all I got. Just as I did before, now I'm going to look at the b value. So my b value is 1. Whoops. And this is a negative, so I'm looking for a difference of 1. So a difference of 11, a difference of 4, a difference of 1. So I must be using 3 and 4. Now I need the difference to be positive 1, so I need this to be a negative 3 and a positive 4. Now when we did this before, we said, okay, let's just do x minus 3, x plus 4, and then equal to 0. And we're almost going to do that, but because it's called amazing factoring, instead of minus 3 and plus 4, it's minus 3 over a. So a is 6, so minus 3 over 6. And this is plus 4 divided by 6. And you might be saying, hold up, why are you making me deal with fractions? Well, I'm not really. I'm not making you deal with fractions because what I can do is I can actually call this 3 divided by 6, which is 1/2. So yes, you will have to reduce fractions. And 4 divided by 6 is 2/3. But now all I have to do is say, okay, I don't like the fractions, so let's bring the denominator out front. 2x minus 1 and 3x plus 2. There's my factorization. What are my zeros? My zeros were the opposite of negative 1/2, so positive 1/2, and the opposite of positive 2/3, which is negative 2/3. Let's look at our second question. Again, it's already set equal to 0, but before I do anything else, I should always look at A, putting things in the correct order, and B, taking out a greatest common factor. So I am going to go ahead and take a 2 out of everything. And then I'm just going to write everything in the right order. So that's 3x squared minus 2x minus 8 is equal to 0. Now I'm going to use amazing factoring on just the inside. So I'm going to look at AC. AC would be 3 times negative 8, or negative 24. Now I'm looking for a difference of 2. So numbers that multiply to 24 is 1 and 24, 2 and 12, 3 and 8, 4 and 6. And again, I'm looking for a difference of 2, and it looks like 4 and 6 have a difference of 2. This has a difference of 23, of 10, and of 5. I need it to be a difference of negative 2, so I'm going to give the 4 a positive and the 6 a negative. And now I'm simply going to write it as x plus 4, but it's going to be plus 4 over a. A is 3. And then x minus 6, so that's minus 6 over 3. I'm going to rewrite this one so that it's not a fraction, so that's 3x plus 4. Keep in mind that I do have a 2 out front that I forgot to copy over. And then x minus 6 divided by 3 is just x minus 2. And that's my final factorization. My final solutions are the opposite of 4/3, or negative 4/3, and the opposite of negative 6/3, so the opposite of negative 2, which is 2. When you start to have 4 or more terms, quite often we're going to be using polynomial long division or synthetic division, and we're actually going to learn that in the next section. But the other way that you can factor when you have 4 terms is to factor by grouping. And when you factor by grouping, you first put everything in the correct order, greatest degree to lowest degree, and then you look at a group and say, does that group have a greatest common factor? So here I would say, and I'm going to use 2 different colors here to make it clear. For my yellow group, it looks like I can take an x squared out of both values. So that gives me x squared, and then I'm left with an x plus 3. And then it looks like here I can take out a negative 4 and a negative 4. So that gives me negative 4, and that leaves me with x and then plus 3. Now stop right there. If these two are not exactly alike, you cannot factor by grouping. They have to be exactly the same. If they are exactly the same, what's going to happen is we're factoring using that distributive property. We're saying, look, x squared has a factor of x plus 3, and 4 has a factor of x plus 3. And so I can take these together and say x squared minus 4 has a factor of x plus 3. And then I can continue my factorization. So what's left? This degree of 2 says I'm not done. That's 2 terms. So I can look at, is this a perfect square? Yes, the square root of x. Is 4 a perfect square? Yes, the square root is 2. I can use a difference of squares pattern to leave me with x plus 2, x minus 2, x plus 3 is equal to 0. And of course, if I needed to find the zeros, it would be x is equal to plus or minus 2, and x is equal to negative 3, simply by putting each of those and setting them equal to 0. Sketching the graph of a polynomial function. Now that we've reviewed all the properties of a polynomial function and how to find the zeros, let's work together to sketch a graph of this polynomial function. We'll start by finding the real roots of the function. So this is where that factoring is going to come into play. We're going to set this equal to 0. There's 2 terms. We're going to start by taking out a greatest common factor. So that gives me an x, and I'm left with x squared minus 4. X squared minus 4, those are two perfect squares, and the difference of them, so that's the difference of squares pattern, x plus 2, x minus 2 equals 0. And then, of course, the important part is to find the zeros. S is equal to 0, to negative 2, and to positive 2. So the first thing I'm going to do then, once I find those zeros, is to plot x equals negative 2, x equals 0, and x equals 2. I'm going to plot those zeros. Then I'm going to think about the end behavior. So this is a cubic function, and we should know that a cubic function will either look like this, or some iteration of that, or going the opposite direction. So which way is it going? Well, because this is positive x cubed, I'm looking at the normal direction, which is down and to the left and up and to the right. Okay, so however you want to determine that, some people just like to put the arrows so they remember what exactly is happening. This side of my function is going to be down. This side of my function is going to be up. So what I have is I already have a pretty good idea of what my function is going to look like. So you can add a few additional points. If I were guessing right now, I would guess something like this. But it's always a good idea to take your entire domain and to separate it into intervals. So by intervals, I mean let's use 0 and negative 2 and 2 as endpoints. If I took my entire number line, negative 2, 0, and 2, and said, what's happening here, what's happening here, what's happening here, what's happening here, I'm going to get a much better idea of what my graph's going to look like. So what if I plug in the point negative 3 and see what's the y value? And what if I plug in the point negative 1 and see what's the y value? And plug in the point positive 1 and what's the y value? And plug in the point positive 3 and what's the y value? Now, why did I pick negative 3, negative 1, 1, and 3? I'm looking for numbers that are to the left of negative 2 or less than negative 2, between negative 2 and 0, so the easiest one is negative 1 unless I went fractions or decimals, between 0 and 2, so the easiest one is 1, again unless I went fractions or decimals, and then 3 or 4 or 5 or so on. So what we're going to do then is we're going to find those additional points. We're going to make up the x values based on the interval. And you can make a little table that looks like this. And here's how we came up with this table. I took those intervals we talked about, from negative infinity to negative 2, from 2 to 0, 0, or negative 2 to 0, 0 to 2, and 2 on to infinity. And I used those same x values we talked about. Then I just used our original function. And I just did mental math. And I said, okay, if I plug negative 3 into that function, I get negative 15. And if I plug in negative 1, I get positive 3. If I plug in positive 1, I get negative 3, and positive 3, I get negative 15. So that tells me that the point negative 1, 3 is right here. Hey, I did pretty well. And the point 1, negative 3 is right here. And to the left of this point of negative 2, it's going to be negative. And to the right of this point, it's going to be positive. So now I can do a little bit better job than I did before by making sure it goes through those new points that I made. So I'm going to get rid of the yellow graph. And so my graph maybe is going to look something like that. I think I did kind of a poor job on this side, so let's try that again. So that's my best guess. And again, we're not doing an exact job, we're sketching. And let's see how I did. It looks like I did pretty well based on the actual sketch of the graph. I wanted you to have a chance to practice on your own. So here is one more of those, sketching the graph of a polynomial. I've given you a quartic polynomial, so it's the 4th degree. I want you to find the roots, determine the end behavior, find a few additional points, and then sketch that graph. Check it against the actual graph to see how you did. When you're ready, press play to see how you did. First, find the real roots of the function. So again, we're just setting this equal to 0. Now, we have 4 terms, and the only way that you and I have talked about in, oops, not x sub 4, x to the fourth. The only way that you and I have talked about how to factor with 4 terms is to have grouping. So I'm looking at groups of 2. The first group has a common factor of x to the third. That leaves me with x minus 1. My second group doesn't really have a factor other than 1, except that it starts with a negative and we don't like that. So we're going to put minus 1 instead of positive 1, which is going to change the sign of x and change the sign of 1. Now if you'll notice when we did that, we did end up with the same factor twice. That leaves me with x cubed minus 1 coming from those 2 outside terms. And then x minus 1 is equal to 0. Now I'm just going to set those equal to 0. So x cubed minus 1 equals 0. So x cubed is equal to 1. So x has to be 1. And x minus 1 equal to 0. Add 1. I get x is equal to 1. So what I have is a lot going on at x equals 1. Remember when we said the multiplicity of more than 1 on an even function? So a multiplicity of 2 would mean my graph's going to come down and kind of do something here and turn around. So that's one thing to keep in mind. Another thing to keep in mind is this is a quartic equation, so it's the degree of 4. So it's either going to kind of look like a W or kind of look like an M, and because it's positive x to the fourth, it's going to look like a W-ish, which just means that it's going to be up here somewhere and up here somewhere. Now on this one, there's really no way for me to know what's going on without finding 2 or more additional points. Because if I had to guess right now, it would look something like this, because there's not a whole lot else going on because we have those zeros. We have a multiplicity of 4, basically, right there. So a few additional points, we find negative 1, 4. Well, that helps me a little bit. 0, 1, that helps me a little bit, and 2, 7, which is off of my graph. So now I'm just going to do my best to come up with something that could be the graph of the function and then check it against the actual graph, and we can see we got pretty darn close. Up next, we're going to look at polynomial and synthetic division, which are ways to find those zeros when we have more terms than what we have already discovered through factoring.